Why is it said that a black hole is not actually a hole? If you were to enter a black hole, the entire process might be completely different from what you imagine. And this journey directly to the origin point of a black hole will be one of the most extraordinary trips of your life. Over the next 40 minutes, you will travel from beyond our world, utilizing various mind-bending physics concepts straight to the core origin point of a black hole. We hope this exploration of a black hole will bring you a delightful mental journey. A black hole, a voracious beast that devours all matter, warps time, an invisible leviathan from which not even light can escape. But you should know, all of that is just the tip of the iceberg. The real story only truly begins the moment you fall into a black hole. Once you plunge headfirst into a black hole, you might encounter the legendary firewall, instantly incinerating you to ashes. You might also tumble into a temporal loop, where past and future blur, or explore a world constructed from holographic information, or even face singularities that might not exist at all. Inside a black hole, space might rotate like a tornado, time might flow backwards, and the aftershocks of quantum chaos ripple outward like the heartbeat of the cosmos. As for the ultimate fate of falling into a black hole, scientists' theories are wildly diverse. Some say you will never reach the center. Some say you will give birth to a brand new universe. Others say you will see your own past or transform into an informational ghost, forever imprinted on the black hole's surface. These aren't wild guesses. They are all deduced from our most advanced physics theories. So please lie back, adjust the volume to a comfortable level, and prepare to enter the black hole in 100 seconds. First, welcome to the black hole. What you're seeing now is the point of no return, the place from which even light cannot escape. Its formal name is the event horizon. Many people imagine it as a sharp edge, but this is actually a misconception, mostly because our perspective on the problem is too narrow. Think about it. The event horizon is not a wall, it isn't even a fixed boundary. This line isn't always just asterisk there asterisk. It's more like a mathematical ghost, a moving phantom. No matter where you observe it from, it might appear different. If you observe from far away, you'll see that as objects fall towards the black hole, the closer they get to the event horizon, the slower they seem to move. This is because gravity is so strong it stretches time itself. The object's shadow stretches, its color reddens, and it grows dimmer and dimmer, until it seems to freeze at the horizon's edge, never quite crossing over. But if you are the one falling in as you cross the event horizon, you won't feel a thing, you'll pass through smoothly. The journey continues for you. This phenomenon is one of the cores of general relativity and is where black holes make us question space-time, and even the act of observation itself. So scientists say, the event horizon is defined by the observer. From afar, it looks like the end of the road, but if you're truly inside, it's merely a part of the journey. This is similar to how we see the horizon on Earth. It looks like a line, but as you sail towards it, it keeps receding. The event horizon of a black hole is much the same, only this time it's space-time itself that's warping. The relativity of the event horizon is not a simple physical phenomenon. Its implications run deep. Hawking radiation theory points out that black holes are not one-way streets. They slowly evaporate due to quantum effects and may leak information. This leads to the famous information paradox. Does a black hole truly destroy information? This goes against the rules of quantum physics. If the event horizon is merely an illusion or an unstable form, our understanding of black holes could be fundamentally flawed. This questioning of the horizon's nature has spawned more radical theories, such as the firewall hypothesis, which posits the event horizon is not a smooth transition zone, but a wall of high-energy particles that instantly annihilates anything falling in. This sacrifices Einstein's smooth transition to preserve the integrity of quantum information. This is a fiercely debated and unresolved point in modern physics. If a firewall exists, your experience of falling into a black hole would be utterly different from the traditional view. But the complexity of black holes doesn't end there. A rotating black hole, a curved black hole, distorts the form of the event horizon even more. Outside it exists the ergosphere. In this region, space-time is dragged by the black hole's rotation. Remaining stationary becomes impossible. Objects must move just to maintain relative stillness. Thus, the event horizon becomes part of the complex interplay between gravity, mass, and angular momentum. Even so, the notion of the horizon as a clear boundary remains challenged. Deep inside the black hole, beyond the event horizon and ergosphere, lies the theoretical singularity, a point of infinite density where physical laws break down. The event horizon shields us from this. Understanding the horizon is key to glimpsing the interior. However, this observer-dependent nature makes us wonder if it's not a solid wall. What would you actually encounter as you approach and try to cross it? This brings us to one of the most contentious concepts in modern physics, the firewall paradox. As you fly towards the black hole, the world behind you seems to stretch and fade. You cross the event horizon line, then, according to general relativity, nothing should happen. No jolt, no flash, no sound from space. Just a dead, silent darkness. This is exactly what Einstein predicted. The event horizon is merely an illusion in space, like a boundary line on a map. But in 2012, some scientists dropped a bombshell that shattered this calm. They said the event horizon might not be smooth at all. It might be a wall of fire. This is the core of the firewall paradox. 3 seemingly correct physical principles: general relativity's smooth transition, quantum mechanics' conservation of information, and the monogamy of quantum entanglement suddenly clash at the black hole's edge. Simply put, if Hawking radiation carries away information, and this information is also linked to the black hole's interior and to previous radiation, then it violates the rules of quantum entanglement. Something has to give. Some scientists proposed that at the event horizon, we must abandon the smoothness of spacetime. In other words, the horizon isn't something you smoothly fall through. It's a wall of fire. Anything that touches it gets burnt to a crisp. In this model, the moment you hit the edge, you're completely annihilated, instantly cremated. This image is terrifying. It directly contradicts Einstein's idea, however. It does protect the purity of quantum information. In the firewall model, Information isn't lost, it is violently vomited out in an intense burst of heat and radiation. The firewall acts like cosmic scissors, snip, cutting the paradox, making the black hole's edge brutally sharp. Many physicists feel the firewall is more a symptom of our incomplete understanding than a real solution. This paradox shows we need a grander new theory, one that perfectly unifies general relativity and quantum mechanics. Others have proposed even stranger ideas, like the fuzzball theory from string theory, which says black holes are actually fuzzy balls of entangled strings, with no traditional event horizon at all, thus sidestepping the firewall problem, or the E=EP conjecture, suggesting entangled particles are connected by microscopic wormholes. Information might sneak through this way. Currently, the black hole firewall remains one of the most hotly debated topics in modern physics. It forces us to think, if you really fell into a black hole, what would actually happen? Would you quietly sink into darkness, or at the edge, experience a swift and violent death? The firewall debate makes us re-examine the black hole's boundary, but the strangeness of black holes isn't limited to their boundaries. For a spinning black hole, the space-time outside it is mind-boggling enough. Take the ergosphere, for example. Imagine a tornado. Now imagine it's not air that's spinning, but space itself. That's the scene around a rotating black hole. This forms the ergosphere, a bizarre region outside the event horizon. Here, it has been observationally confirmed. Space itself is dragged into rotation. Any object, including light, cannot remain stationary. It must rotate along to maintain its relative position. This effect near a black hole is far more extreme than around Earth. This ergosphere is shaped like an oblate spheroid, a flattened sphere, bulging at the equator due to centrifugal force. Theoretically, one can escape the ergosphere, but it requires enormous energy. The extreme physical conditions in the ergosphere even allow for energy theft from the black hole via the Penrose process. Simply put, you throw something in, and under specific conditions, the part that comes out might carry more energy than what went in. The powerful jets from active galactic nuclei might originate from this mechanism. Imagine you pilot a spaceship into the ergosphere. Just before being swallowed, the ship splits. One part falls in, the other escapes due to space-time warping. The falling part carries negative energy, so the escaping part actually gains energy. The black hole slows its spin a bit, and you escape with an energy bonus. More importantly, the ergosphere profoundly affects observation. The paths of light, even causality, are significantly warped here. Light bends and spirals. Objects might appear to move backwards in time, relative to a distant observer, even creating scenes where effect precedes cause. The black hole's spin parameter determines the size and distortion of the ergosphere. The faster it spins, the larger the ergosphere, the higher the energy, and the more extreme the distortion. It might even contact the event horizon, opening pathways to extreme space-time curvature. The frightening part is, initially falling into the ergosphere, you might not notice anything drastic, no violent impact, but you will inevitably begin to rotate. This is the iron law of the ergosphere. Everything moves. You are not just pulled by gravity. You are swept along by the rotating space-time, like a leaf caught in a whirlpool. Helpless, the existence of the ergosphere reveals the complexity of space-time outside a black hole. But this is just the tip of the iceberg. If you truly gather the courage to fall in, what kind of scene awaits us? An even more groundbreaking idea is that a black hole itself might be an inside-out structure. What if falling into a black hole doesn't destroy you but turns you inside out? The inside-out black hole hypothesis is one of the weirdest ideas in modern theoretical physics. This view isn't widely accepted, but it's a serious thought experiment that could change everything we know about the universe and ourselves. The usual story is, the center of a black hole is a singularity, infinite density, where physical laws break down. But many scientists question infinite, seeing it as a sign of our mathematical limitations, hinting at a deeper mechanism like topological inversion. This means the interior of a black hole might be a strange, non-orientable space, like a Mobius strip or Klein bottle, capable of flipping space-time inside out. This hypothesis suggests matter falling into a black hole isn't compressed to a point. Instead, after being squeezed and transformed, it passes through the singularity and re-expands, but into a geometrically mirrored world opposite to ours, a cosmic negative. Here, space-time and even physical laws might be different or inverted. This might explain why general relativity breaks down at the singularity. If treated with more advanced mathematical tools, the singularity equations might resolve, pointing to another space-time. From this perspective, every black hole in our universe could be the beginning of a new universe, birthing new dimensions at its core, forming a nested, matryoshkadal structure, black hole cosmology. This offers a potential answer to where universes come from. In the new universe, the singularity is the beginning of time. Our event horizon corresponds to its Big Bang. The black hole interior is compressed and then outward expanding space-time, similar to the expansion of our universe, where positions and the direction of certain fundamental processes might be reversed. Imagine falling into such a black hole. After crossing the horizon, your perception of space-time distorts. You feel squeezed, but not destroyed. As you approach the center, you flip. Your timeline continues, but spatial directions invert. From your perspective, you are still falling. But in the new, inverted universe, you have just been born, expanding outward from its singularity, becoming part of a new cosmos. If this were true, could our universe just be the interior product of some past black hole collapse? Are physical laws the imprints of a dying star in a larger reality? Testing these theories is extremely difficult, but mathematics can sometimes reveal secrets light cannot reach, revealing perhaps not destruction, but transformation. This inside-out conception drastically alters our view of a black hole's interior. But even if we don't accept such a radical view, just observing a black hole from a safe distance presents a scene that is enough to overturn our intuition. Although we've all heard about the event horizon, spaghettification, and infinite gravity, for an observer, a safe distance in space, the truth is much weirder. Simply put, matter seems to freeze at the black hole's edge. Never falling in, this strange illusion is caused by so-called gravitational time dilation to stronger gravity. The slower time passes near the black hole's event horizon, the point of no return. Time almost stops. If you were to actually fall in, the signals from you would take an infinitely long time to reach the observer. Your movements, your heartbeat, even the light you emit would be immensely slowed and redshifted, eventually appearing frozen at the horizon's edge, never crossing, growing dimmer until invisible. But from the observer's perspective, you never completely vanish. Your last photons are still on their long journey, hence the name, frozen star. What the observer sees is not the black hole itself, but a ghostly shell of infalling matter, frozen at the point of no return. However, for you, the falling observer, everything proceeds normally. You would cross the event horizon without feeling it, and continue your free fall into the abyss. This vast difference between internal and external observation is a peculiarity of relativity. It effectively creates a causal disconnect between different worlds. The mechanism causing the freeze also causes gravitational redshift. Photons emitted near the horizon lose energy as they travel outward, making the black hole appear black. Nonetheless, infalling matter might still leave a faint holographic gravitational imprint near the horizon. This raises questions about the very moment of black hole formation. From afar, the birth of a black hole seems never to complete. This even leads some scientists to question the reality of the event horizon, proposing that black holes might be ever-growing illusions. Hence, alternative models like firewalls and fuzzballs arise. However, the observed behavior of black holes still closely matches Einstein's predictions. For a model with an event horizon, the frozen star phenomenon stems from gravity's extreme warping of time. This time dilation effect is pushed to the limit near a black hole, potentially reaching infinity. To summarize, time compression near a black hole for a distant observer. The falling observer's time slows infinitely, seemingly frozen at the event horizon. For the falling observer themselves, time passes normally, but after crossing the horizon, they might instantly witness the entire future of the universe. This concept of infinite time dilation not only forces us to rethink the meaning of death inside a black hole, but also raises a peculiar question. Could you truly see the end of the universe? Theoretically, if you could withstand the extreme environment, it's not impossible. However, if the black hole evaporates via Hawking radiation, you might never reach the singularity. From the outside, your fall seems never to complete. This makes a black hole not just a physical object, but a portal to an irreversible future, completely severing your perception of time from the external universe. This extreme manipulation of time ultimately leads us to the black hole's most mysterious core, the singularity. But the nature of the singularity itself isn't as simple as we initially imagined. The singularity is not a point. Traditionally, the singularity was thought to be an infinitely dense point, but new physics perspectives like quantum gravity and string theory suggest the singularity might be more like a twisted energy structure or even vibrating strings rather than a dry point. For example, loop quantum gravity posits space-time is composed of discrete units, Under extreme gravity, it might form a high-density region of definite size. String theory reimagines the singularity as a fuzzball, a cloud of knotted strings carrying all the information and mass swallowed by the black hole. This offers a potential solution to the information paradox, and the quantum bounce model suggests quantum effects could prevent complete collapse, causing a bounce into a new space-time region. The singularity is more like a portal to other universes. The key point is the singularity is where general relativity and quantum physics collide and fail. Classical theories break down at extremely small scales, the Planck scale, that is the boundary of traditional physics, and the starting point of the quantum world. Therefore, many cosmologists view the singularity as the limit of current knowledge. If you could witness the scene at a black hole's core, would it be a blinding white light of compressed radiation, a swirling energy storm, or a dead silence due to aberrant light behavior? Even more chilling, if the singularity is a dynamic quantum system with memory and structure. The black hole might store the remnants of everything it ever swallowed. If the singularity is not an infinitely dense point, but a more complex structure, then the question of how it stores and processes information becomes even more sharp. This naturally leads to a more radical notion. The black hole itself might be a holographic projection. Imagine standing before a vast, featureless wall, black as asphalt, thin as paper, but this wall holds all the stories of what happens behind it. Every atom, every star, everything that fell in. This is the essence of black hole holography. Simply put, it posits that information about a three-dimensional world can be encoded on a two-dimensional surface. This view of the singularity as a complex information carrier is akin to a 2D film producing a 3D illusion. Our three-dimensional world might just be a projection of information on a higher dimensional boundaries facing the information paradox. T. Hooft and Susskind proposed a bold idea. Black hole information isn't stored inside, but on its surface. This is the core of the holographic principle. Information is stored on the boundary, not the volume. For a black hole, the event horizon becomes the cosmic ledger, recording all information of infalling matter. This idea suggests the exterior of a black hole might be more complex than its interior. Hawking also leaned towards information being encoded on the horizon. Mathematical support for the holographic principle, for instance using certain theoretical tools, has shown the equivalence between specific high-dimensional gravity theories and quantum field theories on their lower dimensional boundaries. Although our universe isn't such an idealized mathematical space, this success fuels hope that the holographic principle might apply to our universe, at least to black holes. This means if the black holes we see follow the holographic principle, their essence might just be quantum information on the event horizon. Their interior might not even exist, merely a 3D illusion projected from 2D information. Falling into a black hole wouldn't be falling into an abyss, but merging with the cosmic library written on the edge of space-time. The significance of black hole holography goes far beyond. It might be the key to unifying general relativity and quantum mechanics, a Rosetta Stone. Information stored on the horizon implies an astonishing data density. Simply put, every tiny area of a black hole's horizon can store a vast amount of information. This completely contradicts our usual notion that larger volume means more storage. Even more chilling, if the holographic principle is universal, then our own atoms, thoughts, memories, might also just be projections on a distant space-time boundary. This doesn't negate the reality of our experiences, but suggests reality is built upon rules beyond imagination. Black holes, once seen as destroyers, might now be the key to understanding the deeper workings of the cosmos. The holographic principle hints that if a black hole has an interior at all, it might just be a projection of external information. So, if you truly entered this projected interior, how would light and vision undergo unimaginable distortions? At this moment, you are infinitely close to the black hole's interior, and gravitational lensing will be one of the most beautiful effects of general relativity you'll see. It changes the path of light, alters the appearance of the sky, and even lets us glimpse the past. But what would this effect look like inside a black hole? Once you cross the event horizon, the escape velocity exceeds the speed of light. Can light still bend in ways that let you see behind you? Or even worse, see yourself inside the event horizon? The rules of physics changed. Time and space swap roles here. What was spatial distance becomes the passage of time, and time becomes more like a spatial dimension inside a black hole. Light still tries to take the straightest possible path, but in this bizarre geometry, these paths can bend, twist, and loop in unpredictable ways. The gravitational field isn't just a wall, it's all-consuming. Now for the crazy part. Space is so warped that a beam of light could theoretically loop around inside the black hole multiple times before reaching you. This leads to a frightening yet fascinating idea: visual recursion, meaning you might, shortly after falling in, see the scene behind you or even see your own past. If the black hole is rotating a black hole, it gets even more complicated. Photons might get trapped in a rotating photon sphere, circling round and round. Closed light loops might even form, letting you see your own past. Light looping in this way might allow you, after crossing the event horizon, to still see events from outside the black hole. A warped, faded view of the world you left. Add to that the photon sphere, the region where light can stably orbit the black hole. If it exists, models show captured light might swirl in strange ways, forming multiple flickering images of everything that ever fell in. You might hear the final screams of falling matter, see ghosts of other things spiraling into the singularity, or even see your own arms and legs stretched into nothingness over and over inside a black hole. Gravitational lensing isn't just confusing, it's terrifying. Your field of view might become a sphere of flickering images. These images, slowed by relativistic time delay, warped, distorted, and layered like a kaleidoscope. There wouldn't be darkness, but an information explosion, light from everywhere. Some just arrived, some from hours ago, all colliding as you fall towards the most warped part of space-time. In this scenario, a black hole is less a void and more a lens of eternal memory. If you could escape, You might carry the ultimate visual record of a cosmic downfall. Visual distortions and loops are frightening, but for the physical entity falling in, especially a complex structure like you, your physical fate is more direct and brutal: spaghettification. But what would happen to your consciousness? Spaghettification refers to the region around a black hole, where tidal forces stretch matter into long, thin strands, enough to tear apart atomic, bone, even molecular structures. But although we know what happens to matter, beneath the surface lies an even stranger question. What happens to your consciousness as you fall in near a smaller or stellar mass black hole? This tidal force gradient becomes particularly strong. Your feet experience much stronger gravity than your head, stretching your body into an atom-thin strand. At some point, molecular bonds break. Even protons themselves might not hold. But what about the mind? If consciousness arises from the brain, then when the brain is torn apart, is it simply erased? Is your final conscious moment the same instant your nervous system is destroyed? According to Einstein's general relativity, someone falling into a very large black hole might not feel any drastic change at the event horizon. In that case, spaghettification might happen much later. This gives consciousness more time to observe the descent. What would that feel like? Imagine, from your perspective, time begins to slow. The world outside the black hole seems to race by. But you are not. You are trapped in slow motion. Your vision thins like your body, if any consciousness remains. It's like watching the world accelerate as you slowly fade into nothingness. Then the final stretch, when spaghettification truly begins, your sensory inputs would go haywire. Neural signals fail. Vision distorts. The brain, that mysterious gray matter, might remain intact, if only for milliseconds. Could those milliseconds contain a lifetime? Some theories suggest the brain might experience an information flood in its final moments, similar to reports of life flashing before one's eyes in near-death experiences. Trapped in the trap of relativity. From your perspective, your final moments might seem eternal. What if consciousness is not just a product of the body, but related to quantum states? Then entering an extreme environment like a black hole might entangle your brain's final quantum states with the very geometry of the black hole. Part of the mind might merge into the black hole. No one knows. It's just speculation. If your mental information is etched on the horizon or scrambled into Hawking radiation, could part or all of your consciousness continue to exist? Or is the spaghettification of matter also the spaghettification of experience? The final impressions of falling, stretching, shattering into nothingness, played on loop for an eternity, until consciousness completely dissipates under such extreme physical conditions. Not only the fate of matter and consciousness becomes a mystery, but even the predictability of physical processes themselves faces severe challenges. This brings us to the application of chaos theory at the black hole's core. Imagine throwing a feather into a storm. If this storm were inside a black hole, an extreme environment where space-time is violently warped, compressed, and deformed, then even the tiniest initial perturbation could lead to vastly different outcomes. This is chaos theory at the black hole core. The extreme curvature of space-time makes its effects even more pronounced. The butterfly effect might even touch the fabric of reality. The physical laws inside a black hole might fail or become anomalous as matter accelerates infinitely towards the singularity. Space-time paths, geodesies, intersect and spiral in unpredictable ways. An infinitesimal disturbance can cause a particle's trajectory to deviate enormously. Models of rotating curved black holes predict the existence of a Cauchy horizon. Once crossed, predictability has completely collapsed. Determinism fails. Causality is no longer an iron law. This unpredictability might cause space to fold upon itself, creating temporal loops, causal paradoxes, or birthing strange structures like baby universes or wormholes. The randomness of quantum physics superimposed on this space-time chaos makes virtual particle behavior even more bizarre. This is a new kind of chaos, curved space chaos. If you fell into such a core, your experience would be extremely distorted. Spatial sense lost, the sky splits and refracts, light loops form mirages, the passage of time becomes chaotic. Even if consciousness remained, it might disconnect from linear experience. This core chaos poses a severe challenge to information preservation. If information is mixed, amplified, or even replicated here, it conflicts with quantum mechanics' principle of information conservation. Does the black hole's chaotic center hide the answer to the information paradox, or does this precisely expose a fundamental flaw in our current theories? The chaotic core might hide deeper structures, like the existence of multiple worlds. This makes the interior of a black hole even more complex than we imagine. That is, black holes within black holes or deeper level boundaries. After crossing the event horizon of a rotating black hole, you might enter a strange region. Even scientists struggle to explain. Here there might be not just one horizon, but multiple. The most intriguing among them is the inner horizon. This is not a layering of matter, but a boundary where physical laws change drastically within space-time, making the black hole's internal structure complex, like Russian nesting dolls. Unlike non-rotating, uncharged Schwarzschild black holes, rotating Kerr black holes, or charged Reisner-Nordstrom black holes, their internal geometry predicts multiple horizons, including a deeper inner horizon or Cauchy horizon. The peculiarity and danger of the inner horizon lie in its subversiveness. If the outer horizon marks where light cannot escape, the inner horizon might signify the collapse of causality itself. The roles of space and time swap. Known physical laws fail. Predicting the future becomes impossible. This isn't just a mathematical curiosity. In models, the inner horizon acts as a dynamic trap, capable of infinitely amplifying tiny disturbances. As you cross the inner horizon, a single photon could gain infinite energy, forming a mass inflation singularity. Even more astonishing, solutions to Einstein's equations even hint that passing through the inner horizon might not lead to a collision with the singularity, but to a different space-time or even a new universe. A black hole might possess a wormhole throat leading to an expanding new region. The beginning of this region resembles a Big Bang. This implies a black hole could be the seed of a new universe. Each black hole might give birth to a universe with its own physical laws. forming a fractal cosmological multiverse picture. Thus, the inner horizon might be a passage connecting universes, turning black holes from devourers into creators. However, this comes with huge risks. The extreme conditions near the inner horizon mean tiny quantum effects could have huge impacts, even causing the connecting passage to collapse rapidly due to instability. Nevertheless, the structure of rotating black holes, the strange mathematical solutions of Einstein's equations, and some models in string theory all leave room for exploring the inner horizon and its strange possibilities. But if the event horizon, this outer shell, doesn't exist, then discussions about the interior become even more murky. This leads to the terrifying possibility of naked singularities. Imagine the singularity, the black hole's terrifying center, unprotected by an event horizon, open to the rest of the universe. The naked singularity, this frightening idea, is a place where gravity fails. No one can see, and physical laws have broken down. In traditional black hole theory, the singularity is safely hidden by the event horizon. Roger Penrose's cosmic censorship hypothesis proposes that nature hides singularities from us. However, this censorship isn't absolute. Under specific extreme conditions, a naked singularity could theoretically form. For example, if a curved black hole spins too fast, its event horizon might disappear, exposing the singularity. The existence of a naked singularity would be a disaster for physics. Models fail, determinism collapses, causality is confused. It could lead to the collapse of everything from thermodynamics to time itself. Numerical simulations and the inclusion of quantum gravity theory only worsen the problem. Some views suggest quantum effects might eliminate the traditional singularity, but this doesn't rule out the appearance of some equally strange and visible structures. At the former event horizon location, observationally, there is no direct evidence, but some strange high-energy astronomical phenomena are speculated by some astrophysicists as potential signs of naked singularities. If proven to exist, naked singularities would force us to reconstruct general relativity and our understanding of space-time. It might reveal new physics, but the consequences are also extremely terrifying. Therefore, many scientists still favor the cosmic censorship hypothesis. However, rethinking the singularity itself and the fate of information in black holes has also spawned theories replacing the traditional black hole image. For example, the fuzzball theory from string theory. The fuzzball theory abandons the traditional image of a point-like singularity at the center and an empty event horizon. It posits that a black hole is essentially a ball of twisted, vibrating stringy energy. This view aims to solve the black hole information paradox. If a black hole's interior is filled with entangled strings carrying quantum information, then information isn't lost. It constitutes the fuzzball itself. Simply put, string theory says everything is made of vibrating strings. A black hole is just these strings under extreme conditions, forming a chaotic ball of yarn. Information is stored within this yarn ball. Its surface is the stringy matter. Your infall process is more like crashing into quantum chaos than smoothly passing through. The fuzzball theory also offers a potential mechanism For Hawking radiation carrying information, although the fuzzball theory is deeply rooted in string theory, difficult to test experimentally, its mathematical consistency and potential to solve paradoxes make it highly regarded. The fuzzball theory redefines a black hole's composition at the string level. Another equally groundbreaking theory re-examines black hole formation and essence from a higher dimensional perspective. The hypersphere collapse model. What if a black hole isn't the abyss we imagine? What if they are actually curvatures in a higher dimensional space? This is the shocking idea behind the hypersphere collapse model. This theory suggests black holes are not singularities creating holes in our universe, but the result of collapse in dimensions we cannot even perceive. Simply put, the hypersphere collapse model posits that when a massive star collapses, it doesn't form a traditional point-like singularity. Instead, like a higher dimension we cannot directly perceive, it folds to form a hypersphere structure. Its three-dimensional projection is the black hole and its event horizon we observe. This model not only might solve singularity and information paradox problems, but also hints that black holes could be portals connecting different dimensions or universes. Even our universe itself might have originated from a higher dimensional hypersphere collapse. This naturally leads to a grander vision. Are black holes not just the end of a universe, but the seeds of new ones? Black hole cosmology explores this possibility, suggesting the extreme conditions inside a black hole might resemble the early universe. Collapsing matter might bounce and initiate new expansion in a new dimension or temporal direction, forming a new universe. Some theories even suggest this birthing process might work like Darwinian evolution, selecting for universes with specific physical constants. If true, the information paradox is also solved. Information isn't lost, it's transferred to the daughter universe. However, regardless of whether black holes can birth new universes, they themselves are not eternal. Stephen Hawking predicted Hawking radiation, stating that due to quantum effects, black holes evaporate extremely slowly and may eventually disappear in a black hole firework. Beyond Hawking radiation, the quantum nature of black holes might also be glimpsed through gravitational wave echoes. Gravitational waves from black hole mergers captured by detectors like LIGO, their subsequent ring down, if reflected due to quantum structure near the event horizon, could form faint, delayed echo signals. These highly debated echoes, once confirmed, would be direct evidence of new physics operating at the black hole's edge. Ultimately, opinions on what lies beyond a black hole's event horizon differ wildly. Some puzzles seem to make the foundation of physics shake and collapse. As observers, we usually think the event horizon is a smooth transition. If you fall in and survive the gravitational tearing, you pass straight through into the dark core of the black hole. But quantum physics dislikes this story. It dictates information must not be lost. So regarding what's inside a black hole, three different views have emerged: firewall, fuzzball, and freefall. Each paints a completely different picture of what happens when you cross the black hole's edge. What does it feel like inside a black hole? This is the question they all try to answer. First, let's look at the most dangerous option. The firewall. The firewall theory says, at the event horizon's edge, there's a wall of high-energy particles, not a smooth transition. Any object or person falling in is swiftly destroyed. This theory was proposed to resolve some thorny paradoxes while keeping quantum information intact. But the cost is sacrificing Einstein's smooth transition principle. If a firewall exists, you won't just float through the event horizon. You'll crash into a quantum death trap. Now consider the fuzzball, a concept from string theory. According to this view, a black hole is not an empty void with a singularity at the core. Instead, they are made of entangled, vibrating strings, completely filled with quantum fuzz. There's no traditional interior, no singularity, and no event horizon as we typically understand. You hit the fuzz and merge into its structure. The fuzzball preserves information, not by encoding it on the horizon, but by never letting it fall in the first place, then free fall, the classical view from general relativity. According to this picture, for you, the infalling observer, the event horizon is completely harmless. You pass through it unaware. From your perspective, gravity increases, time warps, and you eventually spiral into the singularity. All the mysteries firewall, fuzzball, information puzzle either have no bearing on your journey or only appear from the outside. How do we choose the correct view? That's the real battle, and it's still ongoing. None of these views have been experimentally confirmed yet, but evidence from gravitational waves of black hole mergers and better models of Hawking radiation might tip the scales in the long run. For example, if echoes are found after black hole mergers, they might be signs of quantum structure at or near the event horizon. The monogamy of quantum entanglement is also key to this debate. Different theories have different schemes to address it. This war over the black hole interior might imply our current physics framework is incomplete. Some theorists even believe to truly understand black holes, we might need to step outside our familiar three-dimensional space and consider the existence of extra dimensions. If space has, in more than 3 dimensions, black hole behavior would change completely. Theories like string theory and M theory envision extra dimensions that are curled up and compact. This could cause gravity to leak, black hole morphology to change. Like black strings, black brains, accelerated radiation, or even generate entirely new topological black holes. Detecting extra dimensions might be achieved through subtle deviations in gravitational waves, changes in black hole entropy rules, or correspondence between certain high-dimensional theories and low-dimensional phenomena. Regardless of how many dimensions black holes exist in, when we try to understand these most extreme gravitational prisons in the cosmos, we are, in fact, knocking on the deepest secrets of reality itself. The gravitational waves they produce during violent events are like echoes or chords from the cosmic depths, offering us a unique way to listen, to perceive physical laws beyond our daily experience. So you see, a black hole is far from being a simple hole. If you've made it this far, congratulations. Theoretically, you've successfully traversed a black hole. But this isn't the end of the black hole story. They are where the most important questions in science converge. The more we learn, the stranger they become, if just if. future brings more advanced instruments or perfectly self-consistent theoretical formulas, it might truly be possible to open the interior world of a black hole. Who knows? All right, my friend, let's pause our conversation here tonight on the mysteries of the universe. Now, allow me to press pause for you. Set aside all thoughts and inquiries and simply, quietly be in this moment. From here, my voice will fade away, leaving only the silent tapestry of the cosmos and a carefully chosen piece of pure music tuned to 432 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into deep relaxation. Now, find your most comfortable position. Gently close your eyes or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night, sweet dreams, until we meet again among the stars.